Okay, so welcome to part 2 of my talks. In view of what we said in part 1, which I hope convinced you that there's a relationship between the Ginzburg-Landau functional and the volume functional on the level of their first variations, it's natural to ask whether this relationship extends to their second variations. So I'll begin with some recollections from both sides of the story. And we'll start with the minimal surface, the minimal submanifold side. And we'll recall first the second variation of volume. So we sort of reviewed the first variation of volume in part 1. So let's take a minimal submanifold of dimension k inside of a Riemannian manifold of dimension n. We'll assume that it's closed. And take a vector field on M and consider the flow it generates. Then the second variation of volume can be computed by evaluating this second order derivative at t equals 0. Then you get the following integral. So it's the integral over sigma of the divergence along sigma squared. The formula I'm writing down here works for varifolds as well. You can find it in the paper by James Simons from 1968, or from his paper with Lawson from 1973. So you have and then the second term is actually a second fundamental form term. When you restrict to normal vector fields. And then we have a third term, that's a connection term. So the Levi-Civita connection acting on X, but projecting normally. And finally, you have a curvature term. Okay. So Navla is Levi-Civita connection on M. And these EIs is a choice of local orthonormal frame on sigma. And so all these expressions in integral are independent of the choice of basis, of orthonormal basis, so it's fine. Let me say frame. Okay. In the case of normal vector fields, so first of all, note that the second variation formula, of course, depends only on the restriction of the vector field to your submanifold. And when your vector field restricts to be a normal vector field, then the second variation formula takes the following form. So for sections of the normal bundle, the second variation formula is given by the following simple formula. So you have, again, a connection term. I'll explain the notation in a moment. Minus zeroth order terms. First, you have second fundamental form, and then you have curvature. Okay, so this dx here is just the Levi-Civita connection acting on X and then projecting normally. So it's the induced connection on the normal bundle. And then this term here is the sum, again, over an orthonormal basis of X dot the second fundamental form applied to EI, So the norm of the second fundamental form in the direction of X. The last term, in codimension 1, it gives you Ricci curvature. In higher codimensions, it doesn't. That's, I think, perhaps something you want to be careful about. Integrating by parts gives you the Jacobi operator. So this is Jacobi operator acting on sections of the normal bundle. It's a nice elliptic operator, so you can diagonalize it. It has a sequence of eigenvalues going to infinity. And sigma is stable if the Jacobi operator only has non-negative eigenvalues, or equivalently, if this bilinear form is non-negative definite. And the Morse index of sigma is the number of negative eigenvalues of the Jacobi operator. Okay, so just recalling some standard definitions. Next, I want to recall some classification results for stable and low index minimal submanifolds. Actually, I'll just recall two of them. I'm focusing on the higher codimension case. So I'm choosing to leave out results of this type for minimal hypersurfaces, of which there are many. So there are many results of this type for minimal hypersurfaces. And for a very good survey, I'll refer you to the talks by Martin Lee and also Marcos Cavalcante in the previous edition of this workshop. But below, I'll focus just on the higher codimensional case. The first result I want to recall is due to Simons, and it's from '68, and it's a very well-known result. So on the round sphere, the round N sphere, if you have a non-trivial minimal K submanifold, then its Morse index is at least its codimension. And equality holds if and only if it's a totally geodesic SK. This in particular implies that stability implies triviality. So there are no non-trivial stable minimal submanifolds in the sphere. Here, trivial just means it's the empty set. So the next result, also a classical one, I want to recall, is due to Lawson and Simons a couple years later. So let's take the complex projective space. And equip it with the Frobenius-Judy metric. And suppose you have sigma m inside of CPN. Again, a non-trivial, so non-empty, stable, minimal, and non-trivial. Then m has to be even, and sigma has to be complex. Okay, in the sense that we're assuming that it's connected. So in the sense that the kth power of the Kähler form divided by k factorial restricted to sigma is the volume form restricted to sigma up to changing the orientation of sigma. Okay. So it's again a classification result for stable minimal submanifolds. And in this case, it forces them to be complex. So if this is the first time you see results like this, then let me remark that the converse to Lawson-Simons is true. So any complex submanifold in this sense is stable. In fact, it's a homology volume minimizer. So complex submanifolds attain minimum of volume in their homology class. And it's because of the following computation. So if you look at the integral of the kth power of the Kähler form, suppose it has dimension 2k. Suppose sigma has dimension 2k. Then you can integrate a 2k form over it. By the Vertinger inequality, this is less than or equal to the volume of sigma. And equality holds if and only if sigma is complex in the sense defined in the sense that we're using the word above. This is Vertinger's inequality. And on the other hand, this side here depends only on the homology class. So if you switch from sigma to a homologous submanifold, this term doesn't change. And that's just Stokes' theorem and the fact that omega is closed. Okay, so just from these remarks, you see that complex submanifolds are volume minimizers in their homology class. So complexity, in the sense that we're using the word, is a first-order condition that provides critical points for the volume functional attaining a topological lower bound. And we'll come back to that a little later, but do keep that in mind. Okay, so next I want to turn to the Ginzburg-Landau side of the story and just give you the definition of stability and Morse index, which is very similar. So suppose you have a solution to the Ginzburg-Landau equation. Then we can define its second variation. As follows. So you take a test function v and you evaluate this derivative at t equals 0. And it yields the following formula. Sorry. Okay. And here, by taking the dot product, I'm thinking of these as R2 valued. So I'm thinking of C as R2. Okay. And again, integrating by parts gives you the Jacobi operator, the analog of the Jacobi operator in this case. And you define stability and Morse index in a similar way as we did for minimal submanifolds. Now, where are the vector fields? We'll address that in the next part. Okay. But for now, we'll be happy with this definition. And we can start asking some questions. So first of all, are there results similar to Simons and Lawson-Simons for, say, stable solutions to the Ginzburg-Landau equation? Right? What can you say about stable solutions to the Ginzburg-Landau equation on SN and CPN, for example? Or more generally, can you prove classification results for stable or low index solutions? The second question is recall the, sorry, I should say theorem B here. If you recall theorem B from the previous part, then you can ask how the stability and whether the stability and Morse index of the sequence of solutions relates to the stability and Morse index of the limiting variables of the minimal submanifold generated in the limit. So we'll focus on question 1.